China is poised to revolutionize the nuclear energy landscape. The Asian giant wants to build the world's first thorium-based molten salt nuclear power station, a development that could reshape global energy production.
China is about to change the world forever. What if I told you there is a silver-colored metal with unlimited energy potential that's safer, cleaner, and vastly more efficient than traditional uranium-based nuclear power? This could be the greatest discovery in human history. A discovery capable of transforming economies, reshaping the global balance of power, and revolutionizing life on our planet as we know it. This is the future of limitless energy, and China is leading the way. You gotta watch this video to the end. You won't believe what's coming.
China's latest discovery may redefine the future of energy. Beneath the Bayan Obo mining complex in Inner Mongolia lies a vast thorium reserve capable of powering the nation for 60,000 years. This breakthrough isn't just about securing energy independence, it's about reshaping the global energy landscape. Unlike uranium, thorium is safer, more efficient, and produces less waste, making it a game-changer in nuclear technology. With molten salt reactors, MSRs, in development, China is accelerating toward next-generation nuclear power. But why is thorium so revolutionary? How does it work, and what impact could it have on the world? Let's dive in. Nuclear energy has long been dominated by uranium, but China's recent thorium discovery may shift that balance. Thorium-232, the isotope found in abundance at the Bayan Obo mining complex, offers a more sustainable and efficient alternative to uranium-based reactors. While thorium itself is not naturally fissile, it can be converted into uranium-233, a highly efficient fuel for nuclear fission when exposed to neutrons. This transformation makes thorium an ideal candidate for molten salt reactors, MSRs, an advanced nuclear technology designed for safer and more efficient energy production. Unlike conventional nuclear reactors that rely on solid uranium fuel rods, MSRs use liquid fuel, where thorium is dissolved in molten salts. This approach significantly reduces the risk of meltdowns, as these reactors operate at atmospheric pressure and have passive safety mechanisms. If temperatures rise beyond safe limits, a built-in freeze plug melts, draining the molten fuel into a storage tank where the reaction ceases automatically. This self-regulating design eliminates the catastrophic meltdown risks associated with traditional uranium reactors. Another major advantage of thorium-based MSRs is their efficiency. Conventional uranium reactors extract only a small fraction of available energy, leaving behind large amounts of radioactive waste. In contrast, thorium MSRs can utilize nearly 100% of their fuel, producing minimal waste with shorter-lived radioactivity, making long-term storage and disposal far less problematic. The liquid fuel design also allows for continuous reprocessing, further enhancing efficiency and reducing operational waste. China's discovery of 1 million tons of thorium presents an unprecedented opportunity to tap into this underutilized energy source. Current uranium reserves worldwide could sustain nuclear energy production for a limited time, but thorium reserves, particularly with China's latest find, could extend that capability for thousands of years. China has been systematically positioning itself as a global leader in energy innovation, and thorium research is a key part of this strategy. The approval of the world's first commercial thorium MSR plant in the Gobi Desert marks a major step toward integrating thorium into its national energy grid. This 10-megawatt prototype reactor, expected to be operational by 2029, is designed to demonstrate the feasibility of large-scale thorium energy production. If successful, it will serve as a blueprint for future reactors, leading to commercial deployment across China. The driving force behind this initiative is energy security. As the world's largest importer of oil and natural gas, China seeks to reduce its reliance on foreign energy sources and establish long-term energy independence. The discovery of a massive domestic thorium reserve means China could generate energy for tens of thousands of years without depending on volatile global fuel markets. Beyond national security, China's advancements in thorium energy could have far-reaching effects on the global energy landscape. With fossil fuels still dominating electricity production worldwide, the introduction of thorium reactors could disrupt existing energy markets, reducing the geopolitical influence of oil-rich nations and shifting the balance of power toward countries investing in next-generation nuclear technologies. If China successfully commercializes thorium reactors, it could become the primary exporter of this technology, much like it has done with solar panels and lithium-ion batteries. The emergence of thorium energy also raises questions about global competition. For decades, nuclear energy policies have been centered around uranium. Unlike uranium, thorium cannot be directly weaponized, which may encourage broader international adoption. However, China's rapid progress may pressure other countries, including the United States, Russia, and India, to accelerate their own thorium research programs to avoid falling behind in the nuclear technology race. If China continues on its current trajectory, thorium-based MSRs could redefine how the world approaches nuclear power. Instead of being viewed as a risky and controversial energy source, nuclear power could regain public and political support as a clean, abundant, and fundamentally safer solution for global energy needs. Despite its immense potential, thorium energy is not without challenges. One of the primary obstacles is the technological maturity of molten salt reactors. MSRs have yet to be widely commercialized, and the extreme temperatures and corrosive nature of molten salts pose significant engineering challenges, requiring materials that can withstand prolonged exposure without degrading. Overcoming these technical barriers will be essential for thorium MSRs to become a commercially viable energy source. Economic considerations also play a crucial role. While thorium itself is more abundant and widely distributed than uranium, transitioning to a thorium-based nuclear industry requires substantial upfront investment. Existing nuclear infrastructure, regulatory frameworks, and supply chains are heavily optimized for uranium, making a large-scale shift to thorium a complex and costly endeavor. Additionally, the lack of commercial-scale thorium reactors means that private investors and governments need strong incentives to fund further research and development. Regulatory hurdles present another challenge. Nuclear energy policies around the world are designed for uranium and plutonium-based reactors, meaning thorium reactors do not yet fit neatly into existing regulations. Governments will need to update safety standards, licensing requirements, and waste management protocols before thorium MSRs can be widely deployed. This process will take time, potentially delaying commercial adoption. While thorium reactors offer significant safety advantages, nuclear energy as a whole still faces skepticism and opposition in many countries due to historical accidents like Chernobyl and Fukushima. Educating the public and policymakers about the fundamental differences between conventional nuclear reactors and thorium MSRs will be critical in gaining widespread acceptance. China's timeline for integrating thorium energy into its national grid is ambitious, but it represents only the first step in a long journey. If the 2029 demonstration plant proves successful, China plans to scale up production with larger reactors that could eventually supply a significant portion of its national electricity demand. However, commercial viability on a global scale will depend on continued research, international collaboration, and policy adjustments to accommodate this emerging technology. The discovery at Bayan Obo and the development of thorium-based reactors mark a pivotal moment in the evolution of nuclear energy. The discovery of China's vast thorium reserves isn't just another scientific breakthrough, it's a potential turning point for global energy. Imagine a world where power is abundant, clean, and nearly limitless, where energy shortages and fossil fuel dependency become relics of the past. Thorium molten salt reactors could redefine nuclear power, offering safer, more efficient, and long-term solutions. But the road ahead is filled with challenges. If you enjoyed this video, don't forget to like, share, and subscribe for more updates. Thank you for watching, and see you next time.